to everyone present here. I am Sangeeta Lakshmi, working as Assistant Professor of ECE in R.M.K College of Engineering and Technology. So I am going to start the VLSI design EC8095. So in this, we are going to start the second unit, that is combinational mass logic circuits. So today we are going to start the first session. The syllabus of Unit 2 is we have many circuit families. That is, if you want to design any combination logic circuit, we can have many options: static CMOS, ratio. Like that, we have number of circuit families are available. So we can design any circuit by using different design. And finally, we are going to analyze which one is best in terms of power, in terms of speed and performance. We are going to analyze. So depends upon the application, we can choose any one. Next, we are going to see circuit pitfalls. The second topic in our syllabus is circuit pitfalls. That is, what are all the main things we have to consider for the design. That is a circuit pitfalls. And then power. That is, we are going to see static power dissipation, dynamic power dissipation. Always in VLSI, we have to keep the Taraka mantra. One is speed, another one is area, another one is power. So these three things is the important for any VLSI. So in the second unit, we are going to see how much area is required for each design if we are designing in different logic families, and then what is the speed. Then we are going to analyze power. So finally, we are going to analyze the low power architecture. This is our syllabus in second unit. We will start the first circuit family is a static CMOS. Why it is called as static CMOS means at any instant of time, the output, this output is connected to the supply VGD or else it is ground. So that's why it is called static CMOS. In sometimes they will ask you to derive the, that is sometimes they are asking to realize the any design by using complementary CMOS, means that time also you have to use the same static CMOS. So the generalized diagram is given here. In this, the upper portion consists of pull-up network, which consists of only PMOS. Whereas in bottom, we have the pull-down network, which consists only NMOS. Why it is called as pull-down network? Why it is called as pull-up network? See, this pull-up network is responsible for getting the output equal to 1, logic 1. That's why it is called pulling up. So this network will pulling up to the output to logic 1. Similarly, why it is called pull down network is the output will go 0 or logic 0 if the pull down network is on. So the network which is responsible to pull down the output is called as pull down network, which consists of NMOS. Especially we have to know why the PMOS is considered in upper portion, why NMOS is considered in the lower portion. So always you have to know, if you are using the PMOS is only capable to pass the strong one. Okay, see here I will draw here. I am using this is my PMOS. Okay, so it is PMOS. If I'm giving the 1 at the input, this is my input, this is my output. Okay, so the PMOS, if you want to make it on, means we have to give logic 0 here. Okay, so we have to connect to 0 is nothing but the ground. So if I'm connecting the logic 0 at the gate terminal, this transistor will goes on, right? So if I'm giving logic 1 at the input, logic 1 is nothing but the what? It is VDD. Okay, so if I'm giving VDD here, slowly this this is like a switch, right? The MOSFET is behave like a switch in the throughout the digital VLSI. We are using it as a switch. So if it is on because of this logic 0, what happened? The output will be slowly start to charge from 0. So from 0 to it will charge up to VDD. Okay. So that's why it is transferring the input logic 1 at the input side to output side. Okay, but if we are trying the same PMOS to pass, it is on because of logic 0, but this time you are not going to give the logic 1. Instead of that, you are going to give the 0. 0 is nothing but the ground, right? So you are connecting here, it is to the ground. So due to that, what happened? I need to get the 0 at the output side. But what happened? Initially it was in logic 1. Initially it was in logic 1. Slowly it's nothing but the VDD. Slowly it has to discharge to 0 because the input is 0. If it is on, the 0 has to be get at the output side. But we won't get the exact 0 at the output. Instead of that, we will get some threshold voltage at the output side. Okay, so from this conclusion is the PMOS is able to pass strong 1. That means if we are giving the 1 at the input side, it will transfer the data at the output side. The same one you will be getting at the output side, right? But if we are trying to pass the 0, definitely this PMOS will fail to pass strong 0. Instead of that, we will get some threshold voltage. Okay, so it won't pass as the strong 0. Instead of that, it will pass weak 0. Okay, so that's why the reason why we have connected this PMOS at the upper portion, because the VDD is nothing but the logic 1. If it is on, it will pass as the 1 because the PMOS is capable to pass strong 1. It's very important thing you have to remember. Okay, the similar way, if we are using the NMOS transistor, right? So if we are giving logic 1, then only the transistor will on because it is NMOS, right? So you are connecting here, it is VDD. VDD is nothing but a logic 1. So here you have the input, this is your output. Now you are giving the 0 volts. 0 volts means it is nothing but the ground. So if we are giving 0, what happened? Initially the Vout is 1, that is logic 1. It will slowly start to reduce, right? Because it will on because of logic 1 you have given at the gate. So this will be on. If it is on, the input, the output equal to input, right? It will passes the data from input side to output side. So starting we have here it is 1, but because of connecting the 0 voltage, this will be slowly discharging, it will reach us to 1. So whatever you are giving at the input, you will be getting output side, right? So this NMOS is passing the strong 0. But when you are giving the, that is logic 1 at the input side, if I am giving the logic 1, that is supply VDD, which is nothing but the logic 1, here it is connected to VDD supply, right? So this will be on. If it is on, we need to get Vout equal to the same VDD. But this NMOS will not produce the exactly VDD. Instead of that, it will pass only VDD minus VT. That means the VDD is 5 volts means VT is 1 volts means you can able to get only 4 volts, not 5 volts. So the conclusion here is the NMOS is capable to pass only strong 0. It will pass only weak 1. That's why this NMOS is connected in the bottom portion. If it is on, you will be getting the 0 to the output side. So the NMOS always capable to pass strong 0, whereas PMOS is capable to pass strong 1. This is the conclusion. So next we are going to see how to design the static CMOS, right? See here, I'm taking the example of first inverter. Always the inverter is a reference, basic building block of any digital VLSI. First, we have to start with the inverter. So, I'm going to start the NOT gate, or it is called as inverter, right? So, you know that inverter is nothing but symbol of inverter is this is. The input is, for example, if I'm taking A, the output equal to Y equal to A bar. So, how to design this is, first of all, you have to know how many variables it contains. Only one variable. So, if we have one variable, we need two transistors. Okay. So, one is NMOS and another one is PMOS. So, we need two transistors. So, I have to use always, I told you, just now we have discussed, upper portion must consist of PMOS, right? And bottom portion must be NMOS. So, both the inputs are A. So, I'm going to connect both try together. So, I'm going to give the input A, right? So, in between these two transistors, I have to take the output, that is my Y. Here, always the output we have to take in as the drain terminal and source to the supply VDD. Similarly, the drain of source of NMOS will be connected to ground terminal, right? We have already discussed this. Always the output should be taken at the drain terminal and source of PMOS should be connected to supply VDD, whereas source of NMOS should be connected to ground terminal. So this is our inverter. We are going to check the operation of inverter. So if I am giving input A, what is my output is, as you all know that input is 0, this will invert, that is you will be getting output as 1. If I am giving 1, the output will be 0. This is my operation of inverter, right? So I am going to check this. See here, suppose if I am giving first 0, what happened? Which transistor will on means, definitely if we are giving 0, the PMOS will on. Okay. So if it is on, the VT is nothing but the logic 1, whereas ground is nothing but the 0. So this is on means the switch is closed here. So thereby the path will be created from supply VDD to output Y. So now Y equal to 1. That's why we are getting here, right? Similarly, if I am giving the input to 1, what happened? See here, if I am giving input is 1. So that time what happened? Definitely the NMOS will goes on, right? So the path will be created from ground to output Y. So now the output will become 0. That's why you are getting the output here is 0. So I hope everyone understand this. Inverter means if you are giving 0, you will be getting 1. If you are giving 1 at the input, you will be getting 0 at the output. Okay, this is the simple inverter. Next, we are going to start with the 2-input NAND gate. So this is my 2-input NAND gate. So you know that for 2-input NAND gate, Y equal to A dot B the whole bar, right? So for this, Y equal to A dot B the whole bar. Always you have to remember, we can implement static CMOS using non-inverting functions. Inverting function means the function should be in terms of complementary form. Then only you can able to design static CMOS. Suppose if you have given some equation without complementary form, first we have to convert it in terms of complementary form. Then only we can able to. For example, I will tell you, for XOR gate, what is the expression? For XOR gate, Y equal to A bar B plus A B bar. This is my expression for XOR. But it is not an inverting form, that is complementary form. So what I have to do is, I have to convert into complementary form. So it can be rewritten as, I can write this is AB plus A bar B bar. This is nothing but XNOR function. If I am using complementary of this output, I will get XOR operation. So this is my complementary format of equation XOR, right? So if we have any equation like this, we have to convert here. So directly we can convert like this by using some logical thinking, or else you can use the bubble pushing method that you have studied in the digital electronics. Whatever the circuit they have given, we can convert into in terms of NOR and NAND functions, right? I hope everyone know already this. So now coming to the two input NAND gate design, you have two variables, right? So two variables means we need four transistors. So four transistor means two PMOS and two NMOS, right? Two PMOS and two NMOS we have to use. So here we have the simply I will tell you easily you can remember. If we have the multiplication, in the expression contains multiplication, you have to use a parallel combination of PMOS, right? So I am having here multiplication of A and B. So I have to use the two transistors. One is PMOS, another one also PMOS, which should be connected in parallel. So I have connected parallel combination of these two, right? So this is my pull-up network which consists of two transistors. One input is A, another input is B. And then we are going to connect the pull-down network which consists of only NMOS. The difference between pull-up and pull-down is always you have to use the complementary network. See, in the pull-up network you are using parallel combination, means in pull-down network we have to use the series combination. Okay, so here also the input is A, here also the input is B. It is connected to ground. So ground is nothing but the logic 0 and VDD is nothing but the logic 1. Always the output should be connected at the output side, that is drain terminal. So it is drain, it is also drain, and this is also drain. Obviously the opposite terminal is source here. So it is drain means it is source, and here it is series, so opposite terminal we have to connect. The source of NMOS should be connected to ground. Similarly, the source of PMOS should be connected to VDD. Okay, here also we can verify the operation by the truth table. Input is A, B, output is Y. I am giving the combination 0, 0, 0, 1, 1, 0, 1, 1. So what is my output here is, when I am giving the input is 0, A also 0, B also 0. So what happened here is, if A 0, B 0 means only the PMOS will on, the NMOS will not on, right? So these two transistors will on. See, if both the transistors on, definitely the path will be created from supply to output through this transistor or else this transistor. Any one transistor, the path will be created because it will, the switch, it will on. So you will be getting the output Y equal to VDD, which is nothing but the logic 1, right? So it is correct. Similarly, for 0, 1 combination, what is our output we are going to see? For 0, 1 combination also, any one transistor will on, so you will be getting output as 1. 1, 0 also you will be getting output as 1. If both are 1, 1, if both are 1, 1, this condition alone you will be getting output equal to 0. How it will, we are going to see this. See here, now the input is 1, 1, right? So my input is here 1, here also 1. So in all input A and B is 1. So if you are giving 1, we know that only the NMOS will goes on, right? Because of the input 1, this transistor and this transistor will goes on, and these two will be in off position. So due to that, what happened? The path will be created from ground to output side. So this will be changes to 1 to 0. So for this 1, 1 combination alone, you will be getting output is 0, right? So like this, we can design any kind of circuit, 3 input NAND gate or 2 input NOR or 3 input NOR or any Boolean expression if they have given, we can easily design, right? So I will conclude with this XOR gate. See here in the XOR gate, we have 4 variables, right? So totally we have 4 variables. So I have to use the 8 transistors, right? So 8 transistor I have to use here. So with this, all of you try the XOR gate. This is your homework. If you have any doubts, you can ask. Okay, with this, I'm going to wind up the session.